Hello again, everyone. This is page 5 of Midterm 1 for Chem 3A. So here we go. We're going to do some Newman projections. Okay, so, yeah. Let's see, how do we want to do this best? Okay, so let's number these carbons. Okay, so this is number 1, 2, 3, 4, 5. We're just going to name or number, number the ones that are in the main carbon chain. And at the same time, we're also going to draw in the implied hydrogens that are on carbons 1 and 2, because carbons 1 and 2 are the ones on our Newman projection, and on Newman projections, we have to draw in the implied hydrogens. So we're going to just draw those in, just on the ones that are making up the two bonds of the Newman projection. If you remember, the point in the middle is carbon 1, and this whole circle is carbon 2. So, yeah, we're going to draw the hydrogens on here. So this wedge line right here next to the dash line is going to be one implied hydrogen, and then there's another implied hydrogen behind this methyl group right here. So let's just draw it out, man. Okay, so if we're looking from here, so this is our I. It's looking right along this line. And so we're going to see this methyl group right here on our right, because it's coming out of the page, so that means if we're looking this way, it's coming out on the right. So that's going to be coming out on the right, attached to carbon 1. So that's just the methyl group. You can draw that in as CH3. And so the hydrogen is going to be over on the other side. That's going to be the hydrogen right here. And then we have an OH group going straight down. Actually, let's not draw that right on top of that. Even though it is kind of right on top of it, we want to kind of make sure that we can see both bonds. And then as we can see, we've got, attached to carbon 2, we've got this bond drawn straight down with the epoxide. And we don't have to include the implied hydrogen here, even though it's drawn right here. It's not actually necessary since it's not actually on either of the two carbons, the 1 and 2, for the Newman projection. And so this part is already finished. They actually included the entire structure down there. So we just need to draw the other things that are attached to carbon 2. So there's the hydrogen that comes out in front right here. Nope, that was supposed to be a highlighter. The hydrogen that comes out in front right there, that's going to be right behind this methyl group right there. So we're going to draw, coming out from the circle, a hydrogen. Let's make the CH3 one a little bit longer. Actually, we don't need to write in the CH3. We can just draw a line that implies there's a CH3 there. I don't think we need to write out the CH3. Anyways, so then there's also this methyl group right here up on this picture, and that is right behind this hydrogen. So we're going to just draw another line right here. Let's make sure that this is obvious, that this is the hydrogen, and that's the methyl. We can include the CH3s if you guys want, just to make it a little bit more explicit and clear. And as we said, the substituents on carbon 1 are right in front of the substituents of carbon 2, so they are not staggered. Staggered would be like if instead of the CH3 and the H and this group being here, if they were instead like all moved so that they're right here. You know, like this is an oxygen, and this is the R, and you get the idea. Like this is the hydrogen, this is the methyl. That would be staggered because then they'd each be 60 degrees apart on this Newman projection instead of 120 degrees apart. But instead, we are showing them as eclipsed. They are right on top of each other. Think of like a solar eclipse, lunar eclipse. They are hiding the other. Really, you can think of this OH here as blocking the that whole carbon epoxide group thing, just like the CH3 over here is blocking the hydrogen and the hydrogen is blocking the CH3. We just want to make sure that we're seeing everything, which is why we show them slightly off to the side, but they're still not staggered. They are eclipsed. They're right on top of each other. That's why we can tell that because the wedge here and the dash here that were drawn in, those let us know because we know that the implied hydrogen has to be on a wedge next to the methyl over here. Because if we have a dash group, then we also have to have a wedge group, and so the implied hydrogen has to be on a wedge. And also because of the methyl over here being wedged, that means that the implied hydrogen is behind it on a dash. And so when we're looking at it with our eye going that way, we are seeing the CH3, the methyl group. Let's get another highlighter. The methyl group right here, right on top of this hydrogen. And we're seeing the hydrogen here, right on top of this methyl. So that's why it's called eclipsed. It's just right on top of it. It's kind of blocking it. Same thing with the OH blocking the rest of that molecule. Yeah, so that's that Newman projection. So again, let's number them the same way. We're gonna go 1, 2, 3, 4, 5. But now we are looking from carbon 2 to carbon 3. So this point in the middle is carbon 2, and the whole circle right there is carbon 3. That might be inconvenient to have that drawn in there. So let's just, let's write a little 2 and a little 3 here. So what's attached? Well, see, our eye is looking right there, right along this arrow. So this methyl group right here is going back into the page, which means that when we're looking at it, it's going to the left, coming out of carbon 2. So that's going to be right here. And we can double check that that's the perspective and it's not like upside down or something by looking at what was drawn in for us. We've got this epoxide on carbon 3. We have, so from our eye, we have a bond to the oxygen. This one right here is going down to the right. So let's double check. Yep. From carbon 3, which is the circle, we have a bond going down to the right. And then the bond from the oxygen is going back and it's going to carbon 4, which is, if we're looking down this way, carbon 4 is going to be kind of up above carbon 3, right? So that's why this is carbon 4. Let's label that as carbon 4. And so yeah, that double checks, that shows that our perspective is the eye going this way versus, like, I guess it could be the eye with the eyelashes down here looking upside down. That would be a little tricky for them to do to us, but they didn't. MaryAnn didn't. So, yeah, that just double checked our perspective so we can continue on. But let's go ahead and draw the rest of the substituents on carbon 4 because they started off giving us the epoxide. I don't know why I keep saying they, it's MaryAnn. She gave us the epoxide, but we need to draw the rest of the substituents on carbon 4, which is, we don't need to draw the hydrogen, but we need to draw the carbon and then the R. And I was going through this midterm the other day, and I didn't see this part of the instructions when I was going over it. It says that it doesn't need to count for stereochemistry at sites other than the indicated bond. So we don't need to worry about, like, what shape. If we want to, if she didn't give us those instructions, we can think about it. So from carbon 4, since we're looking this way, it's going to the left because it's going back into the page from carbon 4. So there's going to be that and then the R. So that's technically the right way. Doesn't really matter. Doesn't matter which way this bond is drawn because that's freely rotatable, but it does matter which way this bond is drawn. I guess it would be more correct to draw it this or this way. Oh, I don't know. But it says that we don't need to worry about it, so we don't really need to worry about it as long as it's obvious that we have a carbon there and then the R group. What else is attached to carbon 2? So we drew in our methyl. And then we also have our implied hydrogen right here next to the methyl. That might be a little bit confusing right there. We have the implied hydrogen that is wedged, so it's coming out to the right. And then we have this group leading to carbon 1 going straight down if we're looking at it. So we have that going straight down, and then we don't need to really worry about the stereochemistry right here. OH. Just make sure that this bond is going down and that we have the methyl group and we have the OH. So we've drawn all 3 of the bonds that carbon 2 is making besides the bond to carbon 3, which we don't need to draw because that's just implied by the Newman projection. And we have 2 bonds drawn in for carbon 3. We have the bond to the oxygen of the epoxide and the bond to the carbon of the epoxide. And so all that's left is this hydrogen right here. It's going into the page and to the left from our view and down. So that's going to be right here, coming out from carbon 3, the circle. And so as you can see, this is staggered. They're not right on top of each other. We can double check that in the molecule because we see that, wow, this video is probably getting pretty long. We see that the wedge and dash are both up here for carbon 2 and they're both down here for carbon 3. And so they're going to be kind of opposite shaped, like it's going to be like this for carbon 2 and it's like this for carbon 3. Yes, you can see that down in the Newman projection. Anyways, so that's why it will be staggered. Okay, so last one for this problem, or this part of the problem. So we're going to label again 1, 2, 3, 4, 5, and now we're drawing from 4 to 3, where the middle one is 4, and the circle is 3. Right? Okay, and so let's double check our viewpoint to see which ways our eyelashes are. Are we looking upside down or are we looking right side up? So we see that from carbon 4, the center, we are going out of the page, and if we're looking straight on with our eyelashes on the top, the oxygen is going to the left and down, and that is exactly what's happening on the Newman projection with what we were given. And for the 3, it'll also be going to the left and down from that perspective. So we know that our eyelashes are right here. This is our eye, and we're looking straight on right here. So what else do we have to see? So we have this little carbon and then R group going down into the right of carbon 4. So we're going to draw that like that. R. And then we have a hydrogen going straight up. Okay, so that's everything that carbon 4 is attached to. And then for carbon 3, we've got, so we already have the bond drawn to the epoxide, and then we have a hydrogen there. So we're going to draw, and that hydrogen is going to be behind the, what did I do? Behind this group right here, right? Because it's right behind there if we're looking this way. So that hydrogen is going to be just right here. Well, maybe we should lengthen that a little bit. And there's a hydrogen right behind it, attached to carbon 4. That should be right behind it. And then, so what else is attached to, oh sorry, not carbon 4, carbon 3. What else is attached to carbon 3? We've got this number right here. Got carbon 2. It's going to be going up, because if we're looking this way, it's going above. And so we're going to have carbon 2. That's the only stereochemistry we have to worry about because of the instructions. So we can just draw the rest of it like this with the OH. And yeah, just make sure you have all of the groups you need. And that's also going to be eclipsed. They're right on top of each other. Okie dokie. That's the first problem. Okay, so for part B, it says only one of the 3 bonds analyzed above, so only one of these Newman projections, has the ability to rotate into a significantly more stable conformation. Which one is that going to be? So let's look at each one. So this one right here is eclipsed. Obviously this one can rotate, we can rotate so that it's staggered, and that would be a lot better. We can do 3 different versions of staggered. So that's probably a good candidate. Let's look at the other ones just to double check. So we can rotate the front carbon here, or the back carbon, like one at a time. But the thing is, we've got this really, really big group on the back carbon. This whole thing right here, it's really big. And so it's already in a staggered projection, and it won't be able to rotate into 3 different ones that are going to be better, because see down here we're going to draw 3 different versions that are better, and it's already staggered. I don't really see it getting a lot better because it's so gauche. There's so much going on here. So this is not going to be the one. It's already staggered. It's that's kind of your clue here, that it's not going to be able to significantly get better. Versus the one that's eclipsed, it could significantly get better. We can try the 3 different staggered versions. And then looking at the last one, this one is not even possible. This is the one that you can just cross off the list, because you've got this epoxide between carbon 3 and 4, the 2 carbons on the projection. So if you rotate the back carbon, you're rotating the front carbon with it, or same vice versa. This really, really limits rotation. There's no rotation between carbon 3 and carbon 4. You can't rotate that bond because of this epoxide. So you can't rotate that into a more stable conformation. So we are going to look at the first one right here. That's going to be what we're using for part B. And so it says, rotate the front carbon clockwise, keep the back carbon in the same position as above. So we're going to just draw the back carbon substituents. So we're going to draw this little epoxide right here, and then the carbon, and then the R group, and then we're going to draw the hydrogen and the CH3, And because first we're going to erase that and draw it better because that was ugly. And now, because we're on the iPad, not on the test, we're just going to copy this and paste it a couple times. Because we're keeping the back carbon the same and just rotating the front carbon substituents. Well, really, we're rotating the bond between the front and the back carbon, carbon 1 and carbon 2 as we labeled above. But we're just moving the ones on the front. Okay, so we are going to rotate clockwise. Let's see, clockwise is this way. So we start with the OH down here, but we want all three of the groups to be like this. So we're going to draw, since we're rotating it clockwise, we're going to draw the OH right here. And then we're going to draw the hydrogen, this one. We're going to draw that right here. And then we're going to draw that CH3 group up here. We're going to draw that right here. We're going to go back to this question that says, is this the most stable conformation after we've drawn all the other ones? So let's draw the 3 bonds here again, and the 3 bonds here. And we're going to rotate clockwise again. So we're going to, that is clockwise, right? Yep, that's clockwise. So we're going to draw the OH right here. Oh, why did I write H there? That should have been CH3. That's just a methyl group. Okay. So we put our OH there, then we're going to put our H here, and then this is just a methyl group right here. And then rotating one more time, the OH will be here, hydrogen will be here, and then let's actually erase this so it doesn't look so gauche. And then the methyl group is right here. Okay, so these are the 3 out of, there's 6 possible Newman projections. There's the 3 staggered ones, and there's the 3 eclipsed ones, or those are the ones that we consider the most. I guess you could draw any angle, but those are the ones we consider the most. So these are all of the staggered ones because those are more stable than eclipsed. And now we have to decide which one of these is the most stable. So to do this, we're going to look at Gauss interactions. So we're going to kind of consider the Gauss interactions between a substituent and hydrogen to be insignificant, even though there is some Gauss interaction. We're going to mostly consider the ones between 2 different larger groups. So this is CH3 right here. I guess let's write that in. CH3, CH3, just to remind ourselves, it's not just a little bond, it's actually carbon with 3 hydrogens attached. It's going to be kind of big. CH3. Let's decide where there's Gauss. Okay, so anywhere between a group, 2 groups that aren't hydrogen. So there's Gauss right here. There's Gauss right here. There's Gauss right here. So that's like 3 different Gauss interaction type things. Obviously, there's more between the hydrogen and the hydrogen here. There's like little ones, but we're just going to consider the big ones. For this one, there's a CH3 and an OH. There's CH3, 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 and this number. So there's again 3 different Gauss interaction things. And then lastly, over here, there's one right here, and there's one right here. So Gauss interactions make things less stable. They're all crowding each other, not happy. So we're going to say that this one over here with less Gauss interactions is going to be the most stable. And then the other ones are not going to be the most stable, even though they're more stable than the original one we had for part A. the one up here. They're significantly more stable since that one's eclipsed. They are not the most stable. This one is. Okay. Whew, last one of this page. We're excited here. Okay, so this is a chair conformation. So let's number all of the members of this hexagon. There's 1, 2, 3, 4, 5, and we'll just call oxygen number 6. I guess we don't need to really label oxygen because it's shown on its own. So we were given that star is going to be our 1, and then we're going to go around the chair labeling each one. So what's attached to each one? So carbon 1 has this carbon here, and then it has R2. Here's something to watch out for. Do not just draw a substituent to R2. You have to draw a substituent to carbon and then to R2. You really need to pay attention to where the circles, because that can really get you. You have to pay attention to where the circles start and where they end, because that'll be wrong if you just say that it's R2. You have to say that it's carbon and then R2. So we're going to look at 1, and we see that it's coming out of us into the page. It's wedged, right? And so that's considered an up kind of substituent. So up substituents are either drawn straight up or they're drawn at an angle, depending on what carbon we're on. And so if we are on a carbon that is at the peak of a mountain, or that is an up carbon, it kind of points up. You could draw like arrows too for each one. There's like the down ones and there's the up ones. Just draw little arrows. You see what I'm doing? Like, if that helps you to see. Oh, that's not how an arrow goes. If it's an up carbon or whatever atom, or if it's a down one or up one. You know what I'm saying? So if it's an up carbon or an up atom and it's an up substituent, then it's going to go straight up. If it's an up carbon and it's a down substituent, then it's going to go down at an angle. It's not going to go straight down. It's going to go down at the same angle as one of the other bonds. I'll show you that in another case. And that's going to be equatorial. If it's straight up or straight down, that's going to be axial. And if it's up or down at an angle, that's equatorial. So 1 has the carbon and then the R2, and it's going up. So since carbon 1 is an up atom here, we're going to have the up substituent and then R2. So I'm saying like up and down a lot, but you really need to get in your head if you don't understand it, because it took me so long to understand this. So hopefully this will help. Carbon 2 right here has OH attached and it's down, and over here the 2 is down, right? If you draw an arrow, that's going downwards. So OH is going to go straight down. It's axial. We don't have to label that for these questions, but I'll just label it if you need to practice. So carbon 3, this one is another OH that's going down, but now we're at an up carbon. So this is how it works when you're at an up carbon to draw the equatorial substituents. So you want it to be at an angle going down. So you want it to be parallel to one of the lines, or two of the lines, I guess, of the chair conformation. So if you're drawing it down, you can't draw it on this line, and you can't draw it on this line, and these are each parallel to these lines, right? Like this one's parallel to this one, this one's parallel to this one. So you're going to draw it at the same angle as this one / this one. So your down group has to be parallel to those. Okay? Does that make sense? So So we want our OH substituent. We want it to go down, but we want it to go down at an angle, so it's equatorial because we're at an up carbon, but we're going down. It's going to be equatorial at an angle. So it's going to be parallel to the line between 4 and 5 and the line between 1 and 2. Okay. Carbon 4. Okay, same thing with carbon 1 as far as like we have a carbon and then we have the R group. So make sure you don't just draw straight to the R group. You have to draw a line to a carbon and then to an R group. And so this is a wedge line, so it's going up. And carbon 4 is a down carbon. So again, you can't go straight up. That's just not how the chair conformations work. You have to draw it at an angle, so it's equatorial. Since they're opposite, the carbon is going down, but the substituent is going up. And so again, it has to be up but at an angle. It's not going to be up at this angle between 4 and 5, and it's not going to be up at this angle between 3 and 4. It's going to be up at the angle between 3 and 2 or 5 and oxygen, because those are the only other angles. This one's the same as this. Oh, sorry. This one is the same as this one, and this one is the same as this one. So you look at the other bond, which is 3,5 and 3,2, or oxygen 5 and 3,2. And so that's going to be the angle that we're drawing our up substituent. So we have to draw, here, let's just erase that. Okay, so that's the carbon, and then R1. Okay, hopefully that makes sense. I really didn't get that for so long. There's so many things about chair conformations that can get really confusing. Again, this one, both of these are equatorial because basically they're opposite. So if you're at an up carbon and you have a down substituent, or if you have a down carbon and you have an up substituent, then those are equatorial. But if it's the same thing, like an up carbon with an up substituent or a down carbon with a down substituent, that's when it goes like straight up or straight down and it's axial. And those are way less stable too. So, yeah, that's the 5th page of midterm 1. We're almost done.